I was thinking that maybe I'll try to go through for examples. So to try to avoid being too repetitive with the review, rather than talk about the big theorems or formulas, do as much possible of examples as they illustrate the main concepts. So that often is what's missing. So the concepts are pretty hard, and they're remembering them, or even just remembering them, might be hard because the words every word matters, and they cover a lot of ground at the same time. But having for every concept to have an example of whatever sequence or function that is illustrates it appropriately might be a good idea. We'll see if it works out. I hope you'll have your own suggestions as to what might be necessary. So this is a way. This last example, you can see. First of all, it was. Let me just scroll up. So the goal was to find an example of a sequence. We can't suppose you didn't remember. Okay, so that's what happened. So you didn't remember an example of a sequence that is bounded but still divergent, so no limit. So there are many examples, and if you jump to an example that's not the simplest one, that's okay. But it's still simplest example is the best way to do it. It is a starting where you start thinking. So you're starting thinking about the concept, and a bunch of examples that you might try it on would really clarify things. So we remembered the example here of alternating between -1 and 1. Okay, so that is, if you just look at the picture, you see that there is no pattern, there is no convergence, and then it only takes two values, so it's not running away. Okay, and then this is what happened next is a way to also to reconstruct the function in a specific manner rather than just a picture. So formula important because many computations will depend on it. So and then they see that's how we discovered the formula. Just if you multiply by -1 again and again and again, ultimately you end up with this formula over here. Okay, in fact, okay, there's another question. If you remember the concepts, how do you classify this sequence? Remember classification, not classification of sequences, but there are different classes of sequences, and well, they are just make your life easier sometimes if you just have groups of sequences or functions that are you know how they behave. So what kind of sequence this is? Yes, well, right. That's what we started with the purpose of having a bounded sequence that does not converge. So, once again, where did I put it? So not this is the next one. No limit, but bounded. But that apart from that is certainly the central thing of what we're studying, limits. But what kind of sequence is this? If you every time over here, you can notice that what this is, every time you multiply your previous element by -1. What kind of sequence is that? What if I multiply by 2? Double, 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 double. What kind of sequence is that? exponential, or better term, it is more applicable, the word exponential more applicable to functions. To sequences, a more appropriate term is, remember, geometric. It is geometric, in fact, and something that really doesn't happen with functions, but with sequences you just multiply by the same number on and on. It could be any number, including -1. So -1, this sequence being oscillating, it is, however, geometric. You don't want to call it exponential because of that exact reason. There is no exponential growth. But it is geometric, and because the ratio, so -1, so geometric with ratio -1, and if you keep multiplying by a negative number, it will be very changing sign every time. Okay, so that's the classification of the sequence. So you can say that it is divergent. You can say it's bounded. You can also say, and that's more specific, more narrow, I suppose, is that it is geometric. And there are other geometric ones. So you can, like I said, you can keep multiplying by 2. What happens if I keep multiplying by -2? What kind of sequence is that? Well, just to take a pen and write a few elements. And usually pattern, or often a pattern is clear. Start with any number, say 1, and multiply by -2. What are you getting? -2, and then what? 4. -8. So it oscillates, but with a bigger and bigger swing. So that one is really divergent, right? So not only it is divergent, just like a geometric sequence with a ratio of 2, so that's on the top, it grows exponential, but also it goes down exponentially as well. So another example of what can happen, and the geometric sequences is one of those very fertile grounds for examples. So once again, different behaviors. Where do I find functions that behave in a particular way? Well, frequently one place to look at is geometric sequences. What is the meaning of arithmetic sequence or progression? What's the difference? And so multiplying, what do we do with it? It is simpler. So it's a multiplication, what do we do? We add the same number. So the main difference is like bank. You either have compounded interest, and then you have geometric growth, or decay if you're losing money, or if you just deposit a certain amount of money every month, that would be a geometric growth. The growth then will not be an exponential in type like this, speeding up. It will be a straight line like this. Okay. So anyway, so that is these are kind of well understood sequences. They are determined by only one thing. You need to know the first element in the sequence and the ratio. Geometric sequences, that is, and you'll know whatever there is there to know pretty quickly. You can figure out where it's going, either from experimentation or you have an explicit formula very easily. So the next example was the sequence that is convergent, but not decreasing or increasing. So that might be something that to be remembered. That so it might misunderstandings are often that you just have to have like an asymptote, asymptotic behavior, and for convergence, and it is kind of the case. But once again, all those when we did asymptotes with functions, we saw a lot of rational functions. The rational functions do not oscillate. They do either this or that. Okay, so and then after too many examples of those, you might think that asymptotes are necessarily you approach it from one direction. But as you can see, it doesn't have to happen, especially with sequences. So another example is also, remember this one? How does it work? So add zeros and then you split zeros into 1 minus 1. Remember this? So, and then you remove the parentheses. And then you cancel. Well, you regroup them. Well, let me just cancel them. You regroup them and then cancel. So this is 1 and -1 appears every time in a group, and so they will be canceling each other, and then we're left with just 1. So 0 and 0 and 0 and 0 and 0. Okay, remember this?
Yeah.
Okay.
Use the example of the people digging holes.
Right. Yeah. Yeah. There is. Okay. Let me. I have that. Still have that picture somewhere. I don't remember what it was called. Something from nothing. Okay. Yeah. So that is the same thing, and so it is a cautionary tale about how not to treat infinities. And here we have infinitely many terms, and we carry out simultaneously infinitely many algebraic operations. So that is the cautionary table of what not to do. Otherwise, you don't want to carry out algebraic operation and end up with 0 equal to 1, because that's what we have here. 0 equal to 1, and that cannot be good. So how do we stay away from this trouble? And that is never treat infinitely many operations as if you're doing them simultaneously. What is the way out of this conundrum?
Would it be digging one hole at a time?
Well, I meant mathematically.
Yeah, but
We don't have infinitely many people. Yeah.
it'd be the sense of like doing 1 minus 1 individually each time.
Yeah. Yeah, because that's what it is. If you look at the very top, that's what it is. You're dealing with one hole and one pile at a time, and they are canceling each other for the time being. But if the troublesome step is in the middle, where you suddenly have those infinitely many holes and infinitely many piles put together, combined together into one, and then you may or may not have 0, depending on in which order you will start canceling. And you realize that this is just one thing that can happen. How about I will be canceling, or not canceling, but rather filling? So what if I'll do this? There are some tricky things that you can do. Say brown, and so right now I have only one pile, but you can imagine that what can I have 2 piles?
I guess if you did 2 minus 2 plus 2 minus 2 infinitely, because that would also equal 0.
Well, oh, yeah. So I would do. Here's what I would do. I would take this out. I would take this one and keep it. So that pile will be kept, and this hole over here, you have to fill it. I will use this one to fill it. Okay? So that one is filled. For this one, I will use this pile to fill it. Okay? And so on. Yeah, so then this pile is gone, and this pile is gone, and this pile is gone, but I'm still left with 2. This one is left, and that one is left. Okay? So So that's the tricky thing about infinity, that I can rearrange things in such a way that I have as much left as I like. In fact, I can have infinitely many piles left, or infinitely many holes, if I just do it the right way. It's sometimes easier to explain. I'm not sure if it is easier, but you remember that the alternative interpretation of this, or where this came from, is the Hilbert Hotel. Remember that one? So it's the same story. You have a hotel with infinitely many rooms. It doesn't matter how many people arrive. You always have all the rooms are filled. But it doesn't matter how many people arrive. You can move them, move the people who are already living, and you move them as many rooms down the line, and then you can have as many open rooms, vacant rooms as you like. So it's always filled, and at the same time it is ready to accept as many new guests as you like. So that's the same story. So once again, if you have one new guest arrived, all you have to do is just to move everybody to the next room. So first, who was in the first room becomes the second, second and third, and so on. Okay, and then you have one room left. But if you need two, you just do the same twice. What if infinitely many number of guests arrives?
I think he just broke my brain.
Yeah, it takes a little bit of thinking and getting used to infinities. But the thing is that there are as many integers as many even integers. So you can move a person from the first room to the second, from the second to the fourth, from the third to the sixth. So you multiply by 2 every time. Okay? So in other words, and then from the fourth to the eighth, from the fifth to the 10th, and so on. Right? So everybody's taken care of. Everybody has a room. How many do we have left? Empty rooms. Infinite, because when you multiply by 2, you produce even numbers, which means that all odd numbers, all numbered rooms will be vacant all of a sudden, which means that you have infinitely many guests arrive, and you can take care of all of them all. So these are kind of mathematical games that you play. You have to play if you deal with infinities. We don't really want to do that in calculus as much as fun as it is. So the way out of it is actually how to avoid dealing with those infinities and that pile up is sequences. Sequences is the way to go. So you never treat infinite operation or infinite number of operations, or infinite many number of numbers unless you create a sequence and then look at the limit of that sequence. So that makes sure that to begin with, the order of operations is specific. And that's why first line, third line, and the second line, third line, they are actually different operations. So you in a sequence, you progress from left to right. Then you have to decide what are the elements of the sequence. And the element of the sequence might be, so you can say in that line, this is A1, this is A2, this is A3. Okay? So A4, and so on. So you know which one is which. You know that each of them is equal to 0. As a matter of fact, look at it. Each of them is equal to 0, right? So that's how you know that the answer will be 0. The limit will be 0 because it is a sequence of zeros being added to zeros. Okay? And then, however, if we took the next line, then you have to decide, then the parentheses have disappeared, which means that if you're creating a sequence, how would you describe it? Like this. Oops, say B1, B2, B3, B4. That is a totally different sequence. B5. Okay, what can you say about this sequence?
It's oscillating.
It's oscillating just what we considered. Right, so it will be first 1, then subtract 1, you have 0, plus 1 will be 1, and it will be oscillating between -1 and 1, so the limit is then, what's the limit?
There is no limit.
The limit there does not exist. So as you can see, that transition from one sequence to another changed everything, and we caught it. Why? Because we took the right tool, and the right tool was sequences with sequential operations, and the limit being the limit, and the result of that sequential operation will be the limit of the sequence that being produced. And so in the next line I have say this is C1, C2, C3, C3, C4, and once again we have a sequence, and it will have a bunch of zeros in the middle, and the limit will be 1. Okay, so that's the third possibility. In the middle, that is, you have a divergent sequence in the middle, and that is a no-no. So you will never replace a divergent sequence with its limit, because there is no limit. So the first sequence, it would be, in a sense, legitimate to replace it with its limit, which is 0. The last one also okay, because it has a limit, it's 1. Okay, so but if in the middle there is a sequence that has no limit, it means that it is not a number, and it cannot be subject to any algebraic operations to begin with. So, and it cannot be part of any kind of computation. So there is no possibility of these being equal to each other. So it's a cautionary tale, and we learned a lesson, and that will come up in Calculus 2. This is, in fact, these are not really sequences as much as, well, they are sequences, but the proper term is series in Calculus 2 when you do addition of term by term in a recursive manner. Okay, so but that's the bad news. A bad example. A good example of convergent sequences that was very helpful is the decimals. So same story, except it works out. So you have say, well, you might remember this controversy if you ask for 0.999 equal to 1. Is it? No? Well, the only way, once again, to interpret anything that has that business, it means that there are infinitely many digits there, and the only way to actually understand it is to do what? The same thing, sequences. So this is 1 is okay, so there is no much to be told about it, but 0.999 is understood as a sequence. So it is a sequence, understood as a sequence, and once you see it as a sequence, then you know that if you know what that sequence is, or end up to be, you take its limit. So 0.999 is the limit of well, what's the meaning of it, of the sequence? It is its limit. So its limit is 1. Okay, so they are equal to each other. So the answer is yes, they are equal to each other, but in what sense? In that sense. So even though every truncation of our number on the left, doesn't matter how many 9s you take, if you stop at some point, it will be strictly less than 1. So it is not equal to 1. But if you continue on with the sequence, and so you have a1 is equal to 0.9, a2 is equal to 0.99, and so on, this sequence will converge to 1 and goes to infinity. Not really that hard to demonstrate. Why? Because if you subtract, remember how we evaluate limits, we subtract the sequence minus the limit. Okay, so an minus 1 will be equal to what? A bunch of zeros and 1. So n zeros here, and that thing goes to 0. So that's how we know that the limit is 0. So that's once again another example that illustrates the use of the of sequences and resolving an issue like that. The same that appears later on. Once again. So it's like a controversial question in the sense that if you go to any kind of math help forum or anything like that, that you will be bombarded with questions like that. Another question that appears is 0 divided by 0, or 0 in the power of 0, and things like that. Okay, so what's the answer to those? How do you make sense of these? You say indeterminate if somebody throws at you 0 divided by 0, you say it is indeterminate and that such is meaningless. However, in your own computations, if you encounter 0 over 0, you should not say indeterminate stop, because there is some background there, and typically behind every number, when you end up with something like that, there's another sequence or function, right? So so those two zeros are in fact limits, probably. So it could be, say, 1n divided by 1n. Both of them are going to 0. And does it mean it's indeterminate? No. 1n divided by 1n is what? Well, 1n divided by the same exact number. What do you get?
Would be 1.
It will be 1, that's right. So that is the meaning of 0 over 0. Could be 1. Could be. It doesn't have to be, but it could be. So that's the meaning of indeterminate. If you think about it, it's just indeterminate because there are so many possibilities, and on the surface you cannot tell what it is. But if you go back and see where those numbers came from as limits, then the answer could be as simple as that. And certainly we can think of other examples that gives me, for example, if I have 1 over n divided by, well, 1 over n squared divided by 1 over n. Well, so once again, 0 is 0, right? However, if I divide, I end up with 1 over n, and this one goes to 0. Okay, so 0 over 0 could be 0 too. And there are just so many possibilities. There are so many possibilities. In fact, every single possibility is a possibility. So every number, as well as infinity, including 0, as well as infinity. So once again, that is something to watch out for. So all of this also has numerical underpinnings, and you can see those behavior and patterns pretty quickly, but sometimes you don't see. Sometimes the patterns takes too long to appear, and so that's why we have to do this. If we are interested in absolute infinite accuracy, we have to take limits and find them, and without experimentation, because experimentation might cause us to make wrong conclusions. Okay, so what else? So once again, examples of limits are very important. Sequences. So the more examples you know of sequences, the better you can understand the limits. Because you can just apply the idea to every sequence one at a time and see how it works out. Okay. Properties of algebraic properties of limits, usually not a problem. So sequences can be combined together through addition, subtraction, multiplication, division. Okay, so that's pretty much it. So that usually doesn't cause a lot of problems. So sum rule, product rule, quotient rule, things like that. They're very predictable. If you remember, whether you remember or not remember the geometric interpretations of that, what you might be doing with those sequences, either way, if you come across such a computation, you probably shouldn't have any trouble doing it. Just the way I did it over here. The only thing that you should think about when it's final exam, that you have to quote. You have to quote as much as possible those rules. and the composition rule. So the composition rule or substitution rule. So it's most probably the trickiest one. So say limit of sine 1 over n goes to infinity. Okay, so it's not summation, no subtraction, multiplication or division. So we're talking about what here? So we talked about those four operations, algebraic operations that we have, and they have four rules: subtraction, addition, subtraction, multiplication, division. So this is not one of those. So what operations are we talking about before you get to the limits? So substitution rule of limits. But you have to identify the algebra that you're facing before you can think about limits. So what are we talking about here? What? Yes, but what is you have trig function sine, and then you have 1 over n, a sequence. So what's the word? Well, another word for substitution. The fifth operation on functions. What? What? It is. Yes. It is the composition. It looks a little bit different from what we have seen recently, because sine is a function and 1 over n is a sequence, so you do a composition of the two. But so I was just about to give you an example of something like this. Okay, that would have been or sine 1 over x, better yet. An example of composition which was more transparent in that sense. But as far as even if you don't want to call it a composition, then the substitution certainly is applicable, because we have sine, and then we substitute 1n into it. Every time you have a substitution, it's important to remember that word. The composition is long term is a better word than substitution, even though substitution is a kind of a more revealing and descriptive in a sense, but just the proper terminology is composition. And all year there are just so many rules. The composition will appear more often than the rest of the operations, because composition, any two functions can be combined with compositions, just about any as long as the input-output match. But addition, subtraction might go away, because you're dealing with functions of a nature that is not numerical anymore. So once again, that senators example from yesterday and from before, you can see a composition of that function with a lot of other functions, but you cannot do addition, for example. So remember, the function was from the senators to states. Yeah. So you could have a composition from from states to their population, if you might remember. That could be, so the composition can be formed. What cannot be done with it, you cannot add these functions. So the function from senators to states is not subject to any algebraic operations that we know, because there is no algebra, there are no numbers, and therefore there is nothing to add or subtract, multiply or divide. Compositions still are possible. So compositions are work throughout functions of any nature. So anyway, so it's a composition. Once we identify the composition or substitution, then what do we do with this limit? Well, you kind of, yes. You don't really take the limit of the sine as much as you substitute the limit of 1 over n, that's the part about substitution, into the into sine. So the answer is this. Okay, so like I said, on left, what we have on left is that the sequence 1ON is substituted in sine, forming a composition. Okay, but on right, it's still about substitution, except we're substituting the limit of the sequence rather than the sequence itself. And that simplifies our life, because the limit of 1ON is 0, and we have our answer. So what's missing in this solution? So, well, as I just said, that when you applying rules, you have to quote them. So if you just submit this, that would be incomplete. So to begin with, well, one part that is incomplete, that you have to quote the substitution rule to justify the transition, but there are also more to be said. Remember what those words are? Magic words to justify transitions like this. Because what? No, chain rule is differentiation. No, the substitution rule does not work with all functions, but of functions of nice kind of functions. What are they? What's so special about the sine?
Trigonometric functions?
It is trigonometric, but as trigonometric function, I could have used other functions here. I could have say limit of E1ON, or I could have limit 1ON squared. Okay, so all of these are subject to the substitution rule, but why does it work? So once again, you see I'm applying the substitution rule again and again to different functions, exponential function in the second example and the square function in the next one. So it will be what is it? Limit 1ON squared. Okay, you see how it happens? How I pull out the limit sign inside of the parentheses. So I am pulling out inside the parentheses, which break the composition. So instead of having a composition, these are compositions that we're dealing with, well, they disappear on right, thanks to the substitution rule. But you cannot apply substitution rule without justifying it. So because it does not apply to all functions, but only what kind of functions? So trig functions, good. These functions, the square function also. So what are the magic words? Sine is, just scale it down from differentiable. What's the, another good word, not as good as differentiable, but starts with a C. Because the sine is continuous. So all differentiable functions are continuous, but not all continuous functions are differentiable. So sine is both, and but it suffices to say that it is continuity is sufficient. And so exponential functions continuous as well, and square functions continuous as well. So all the functions that we know pretty much are continuous on their domains. So all trig functions, even tangent is continuous as long as we stay away from its vertical asymptote, where it's undefined. The same with the rational functions. They have all of those holes in the domain. As long as we stay away from that, we have everything is continuous. The point is that you have to speak these magic words. So every time is about limits, and you have substitution rule for whether it is limits of sequences or functions. The words are the same, and that is the the continuous. The function is continuous, so we can substitute, and that's why the sine of, so x is approaching 0. Okay, so what happens to the sine of x when x is approaching 0? It is approaching the value of sine at 0, which is 0. Okay, so that is an example that we saw a while ago. So this is what sine looks like, and then we ask ourselves what's happening when x behaves like this. It is approaching 0. What's happening to y? And the answer is, well, it is approaching 0 as well. So y is approaching 0 as well. Okay, so that's the continuity. When the particular behavior of y also forces, a particular behavior x forces y also behave in the same nice manner. So accumulating of x towards 0 causes y to accumulate towards 0 as well. Okay, so or any other number. Okay, so that's the essence of continuity, which is not directly applicable to sequences, but it is very convenient for both finding limits as well as explaining the meaning of continuity. Okay, so then what becomes important is knowing all the continuous functions. The answer is pretty much, unless a function is made up of pieces, remember piecewise defined functions, then all the functions that we have are continuous on their domains. So that's something to, I guess, easy to overlook. So typically, so I cannot be more precise here, but typically functions are continuous on their domains. So remember, continuity is studied one point at a time, and so as long as that point is in the domain, the function is probably continuous of all functions that we know. But if we may start make up functions from pieces, then certainly that something like this, it's very easy to make up a function that's going to have a gap and it's not continuous. But any kind of a familiar function, that nice function, classes of functions that we've seen, they all satisfy this property. So they might be made of several pieces, but these continuities are also points where the function is undefined to begin with. Okay, so infinity over infinity, I'm not going to talk about that again, but it's the same problem as here, and it's another indeterminate expression. And once again, once you run into it, the only way to resolve it is drop it, go back, think about your limits, and probably there is somewhere, if in the end of the computation you have infinity over infinity, it means that at some point you just pretty much went in the wrong direction. So then you go to algebra and simplify things. Okay, comparison tests, remember those comparison tests, squeeze theorem. Well, this one is a kind of a theorem that is more advanced, so I'm not sure if you remember, but a sequence that is bounded and monotone converges. So a sequence that is monotone cannot won't oscillate. So that's the good thing about monotone sequences, that it's not going to do this. Okay, so that the kind of really bad kind of a divergence is out of the question. The worst thing that can happen when you start like this, that it will go to infinity. When it is bounded, then it cannot happen, and then through some proofs in magic of mathematics, there is a limit somewhere. So limit is somewhere. So eventually it will approach some number. So bounded and monotone, increasing or decreasing. Okay. So there is this also a bunch of famous limits, as I like to call them, That's probably a good idea to remember, so let me just write them out. So the final is coming, and then there will be some of the things that you need to remember. They quite a lot actually. So this one is probably might come up again. So limit of sine x over x. Do you remember what this is? No. No, it's 1. It is, in fact, you're comparing a sine function, which is, they say this is sine, and what? And a function that looks like this. So y equals sine x and y equal x. So you're comparing them, and what the limit says that they are pretty much what? What's the relation between sine function and the y equal x function? What's happening here?
They both pass through the origin?
They surely do, yes, but we are saying more than that. The relation between this straight line and this curve. It is the tangent. That is the answer. So is tangent, and that's what this limit says. The limit says that sine and y equals sine x and y equal x are tangent to each other. So one of them is curved, the other one is line. So technically it is a tangent line. So a tangent line, and then we certainly, since we're doing review, we can also just it's useful to realize that this famous limit is also equivalent to simply saying that sine x prime at 0 is 1. So the slope of the sine function at 0 is 1. And that is exactly the same to say that this y equal x line is tangential to the curve. Another one, very similar one, it is cosine x minus 1 over x. The same exact story. The limit is 0, however. Limit is 0. Once again, this is my cosine, and the tangent at 0 will be, in fact, horizontal. Well, there is one more. Well, what is it? Remember this one? It's e. So it's a kind of exponential growth, which is kind of being averaged at compounded interest. That is compounded interest compounded continuously. So so just a limit, and so we certainly don't have time to actually talk about compound interest right now. But that's where it comes from. Things that are more troublesome, I don't expect to have a lot of it, but you never know. And that is the algebra that's not technically part of calculus, but it comes from pre-calculus, and that is the certain properties of trig functions, property of the exponential function, the logarithm. All of these might come up in some way. So the properties are only for trig functions. You don't have to remember many of them. You just need to know the tangent is sine over cosine, something like that. And plus, what's the number one property of trig functions? the Pythagorean theorem, right? Sine squared x plus cosine squared x is equal to 1, and that pretty much, most of the trigonometry is here, and the rest is derived from it, and I don't expect you to need for anything beyond that. However, remember, if you go with exponential function, then there are all kinds of properties. So x plus y is equal to what? That's right. So this kind of property you need to remember, and they have only for the exponential function, and there is the same for the logarithm. So it is certainly, hopefully, you made some progress in that direction. Okay, so the next thing to review for us is limits of functions. We already started with limits of, with continuity, and it is probably an okay idea to, in spite of the way we did it, to understand limits through continuity rather than vice versa. So ideally, you understand limits first of functions, and then you understand continuity. But I mean, when you already pass that, and you're trying to create some kind of a solid picture in your head, then they are kind of so they might merge together. It's not such a bad thing if it does happen. So once again, the functions might be discontinuous, but then the limit might exist that the function is discontinuous. Okay, so such as this. But it is more like an exotic example like this. It's not hard to come up with this example that, once again, the limit at this point exists, but the function is not continuous. So it does happen. In fact, it's very easy to think of, say, x squared minus 1 over x minus 1. That's the example of such a function at x equal 1, has a hole in the domain, and then you add one extra value. The limit exists, but the function is either undefined or discontinuous. That doesn't matter. So that's a possibility, but other than that, continuity is just a good way to think about. If you think you understand continuity, then you should use it to understand the limits of functions. But there are many interpretations of limits of functions. So that's something to keep in mind. Okay, so the limits of functions. So initially, the limits of functions are thought of only as at a point, and let me just give you that. The definition is really not complicated. So f of x goes to L as x is approaching a. What does it mean? It means that xn converges to a implies that f of xn converges to L. Okay, so that's the definition. So you can see how we are using the limits of sequences in order to understand limits of functions. So the last line, you're looking at two sequences, well, for any sequence, xn. So if you understand sequences of limits of sequences, then you are in a good position to understand limits of functions. So that's what the second line is. The two sequences, one converges on the x-axis, the other one then has to converge on the y-axis. That's what we're saying here, and that's what creates a convergence of a function as a whole. So all the sequences converging to A will be transferred or transition into convergent sequences on the y-axis. So once again, this is on the x-axis, and this is on the y-axis. Just like the picture that I had, like not this one, this one. Okay, so convergence on the x-axis forces convergence on the y-axis. So either this is a limit, or how do we get continuity? it is when L is equal to f of a particular value. So there is no hole in the middle like there. So not only limit exists, but it is a particular value. And then you turn around and you later on, when you know this is later on. Okay, so that then we have already done it, and now we just have to integrate it into our thinking. Is that ultimately for computations, we, instead of trying to figure out whether a function is continuous or not, we already know which functions are continuous, and we use that fact in order to compute limits, which we did just a minute ago. So everything is built gradually, and that's why this is a starting point. But really, at the end, this is where you want to be, this one. So using continuity to compute limits rather than vice versa. So, but then you just need to know, understand continuity as substitution, pretty much, and then apply in this manner. But there are other important conclusions that we draw from continuity of a function, starting with, remember, the graph is continuous curve. So if the function is continuous, then its graph will look like this. Okay, so it does not break. So that's how I suppose the payoff of this work with limits. Then we understand what it means for curve to be unbroken. We can explain that, we can compute it mathematically. Okay. And then you remember all kinds of things come up as well elsewhere when continuity comes up. For example, most recent was continuous functions are integrable. Okay, so that's good news as well. Okay, so we'll skip one-sided limits. Remember what those are. So once again, algebraic operations and limits. So this one, and then once you're done with that, you have the substitution rule for limits, but this time for sequences. And it looks exactly the same. That's the good news. So for example, if I'm looking at this limit, then it doesn't really matter, do I have a sequence or do I have a function? So how should I put it? Let me go here. So say, so substitution rule again. So the big part of the substitution rule is, well, two big parts of challenging things is, number one, compositions, and number two, continuity. But otherwise, this is the limit of, say, sine x squared as x is approaching 0. What do? We do the same thing we just did. We pull limits inside and sine outside. So I'll have sine with limits inside of the function. Okay? And then naturally they simplify things. So one complex limit with two functions involved now becomes the sine is out of consideration until we're done with the limit inside. We don't worry about it. So it will be sine x squared goes to 0, and so we have 0 right away. Okay. Well, just as with the limits of sequences, you have to justify it. You have to mention the substitution rule, and you have to say those magic words. And what are they? Sine is continuous, right? If you want to be specific, it is continuous at x equals 0. But it's continuous everywhere. So quotient rule, sum rule, all of that is fine, I suppose. Shouldn't be a big problem. Okay, so what else? Indeterminate expressions, we know how to deal with them. There's really no difference in treating sequences or functions in that sense. It is always, there is some kind of algebra mistake that you made, and there's always a way to resolve it. So indeterminate expression might end in any number infinity, the other infinity, or it could still, limit still might not exist. So every possible answer is there, might be hiding there. So there might be some computational things as well. So discontinuity is, I guess, a long-term lesson is that discontinuity is to be avoided if possible, because it's probably if you have some kind of model and then you have, and you know there is some continuous process there, and then you discover your function is not continuous, then it's probably there is something wrong with your model. So abrupt changes of input produces, well, I mean rather continuous, very small change in the input produces a dramatic change in the output. So that's usually not good. It is like what is it? Straw that breaks camel's back. Okay, so that shouldn't happen in any kind of modeling science and so on. Even though it does happen, but you should be aware of it if it's coming. So so if you were building or designing a bridge, you probably should be considering the strength such a way that you were nowhere close to the possibility that one extra car on it will make it collapse. So that certainly is not something that you want to face, but mathematically it's also really a breakdown. Piecewise defined functions, those are man-made functions, and they are frequently either discontinuous or they are or at least non-differentiable. Okay. Continuity is preserved under algebraic operations. Once again, as long as you don't divide by 0, you have addition, subtraction, multiplication, and division. Trig functions are continuous. So remember, they are pretty much shadows of you have a stick and sticking out of the ground, and then the sun leaves a shadow on the ground, and that shadow will be a trig function of what? Of the angle of the sun above the horizon. So that's why it kind of explains why the function is expected to be continuous, because you can almost see it like there is a motion of the sun, and you can see how the shadow is changing. It does not change abruptly, unless the ground is uneven. But suppose it is even. Okay, so maybe I'll just stop here and we'll just resume tomorrow. And so once again, try to think about what you might want to talk